Hello friends and welcome to average classes. Okay, so last class we have discussed your simple manometer. Okay, so today we will be discussing your differential manometer. See what happened in your simple manometer. So we have a piezometer, we connected that. Okay, then we have a YouTube manometer, single column manometer. Okay, and vertical and inclined manometer. What was there is single column, your simple manometer can only tell me the pressure of the point where I am going to attach that, where I will attach that. There only at that point only it will tell me the pressure. So slowly the technology developed and we came to the differential manometer. Differential manometer, now I am able to find the difference between two pipes, the difference in pressure between two pipe lines. Okay, single column manometer, throughout any location of the pipe if I will connect, whether the water or the liquid or the fluid flowing there is stable or or flowing or static, it will give me the same reading. Here what? Now these are two pipe. There is pipe A, there is pipe B. Okay, and we can find the pressure difference between these two pipes. Okay. So today's topic is that, and if you haven't subscribed to the channel yet, please do subscribe. Okay. Chaliye. Okay, so first thing is, this is differential YouTube manometer. First you should know, sir, it's a manometer. Manometer means it's a pressure measuring device. It's a pressure measuring device. U-tube means this U in shape. The shape of the tube is U, English letter U. Okay. Differential means it will give you the difference in pressure. Means this will give you the difference in pressure. Hence it is known as differential YouTube manometer. So today we will be discussing your two cases. One is your YouTube differential manometer, vertical and inverted YouTube differential manometer. This is YouTube as the letter U, English letter U, sorry, as the English letter U. This is inverted U. Okay, this is inverted U. Okay, cool. Now let's come to your vertical YouTube differential manometer. So there are two pipes, pipe A and pipe B. Okay. Let us say initially I have not connected this. Initially I have not connected the YouTube to the pipe. Okay, YouTube to the pipe. That means I have some what? I have some YouTube, your manometric fluid. Let us say the manometric fluid was up to this. Okay, this is your manometric fluid. You know, horizontal level, they will be at same horizontal level. They are going to be at same horizontal level. Let us say the gas or something in this A is having a density rho 1. Okay, and here B also I have some gas. B also I have some gas. Sorry. So okay, wait. Give me a moment. Very good, So your differential YouTube manometer. So here we have a density rho 1 at pipe A. Pipe B, we have a liquid. We have a liquid which is which has a density how much here? Rho 1 rho 2. Okay, which is rho 2. Now we have a manometric fluid and the density of manometric fluid be rho m. Now what we do? This YouTube manometer I have gone and I have connected to the pipes. Two different pipes. Okay, I have connected to the two different pipes. Now as soon as I will connect, what will happen is, okay, this liquid will come here. I am assuming the pressure at A is greater than pressure at B. I am assuming the pressure at A is greater than pressure at B. So this will apply some pressure here now. Wait, on the manometric fluid. Because of this manometric fluid will try to lift. This manometric fluid will try to lift on the right hand column. Okay. Now here also B also will apply some pressure. B is going to also apply some pressure. So what will happen? This manometric fluid it will be rearranging. There will be a movement. There will be a movement, and after some time equilibrium will be reached. After some time equilibrium will be reached. Equilibrium reached means what? The pressure on the left hand side and the pressure on the right hand limb will become equal. I have already assumed PA is greater than PB. So let us say after some time this portion decreased a bit. Here it decreased a bit. Okay, after this it decreased. So this is mine, and here it got increased a bit. Let us say it got increased. Okay, so this is the difference in height of manometric fluid, which I am writing HM. Okay, and let us say this is the height H1 and let this be the height H2. Okay, let this be the height H2. Okay, clear? Got it? So how many fluids we have? We have 3 different fluids. Now what? Now we'll write the gauge equation. That is, the pressure on the left hand side is equal to pressure on the right hand side. Now we'll write the gauge equation. Okay. So write. Before that we have to take a reference line. So always the gauge equation we write on a reference line. Reference line makes our work easier. It makes the formula look simple and makes our work easier. See, suppose I can write the equation here also, at the bottom line also I can write the equation. But I want to make the things more and more easy. So what I'll do, I'll take the help of Pascal Law, which have told me if there is a continuous mass of fluid, continuous homogeneous mass of fluid, so the pressure at both will be same. So in a horizontal level. So pressure at this point L is equal to pressure at this point R. Okay. So the pressure on the left limb at L equal to nothing but this pressure, that is PA plus the pressure because of this height. What is the density I have to? Rho1 G height H1. So the pressure on the left hand limb equal to pressure on the right hand limb. Right hand limb what I got? PB plus this height, that is Rho2 G H2 plus the manometric height. Okay. So Rho m G Hm. Correct. Now I need difference in pressure. That is PA minus PB. I need difference in pressure. PA minus PB. So what I got? Rho2 GH2 plus Rho m GHm minus Rho1 GH1 minus Rho1 GH1. Okay? Understood? Okay. So this implies now what I am doing. I already got my desired equation. This is my equation. Okay, this is my difference in pressure. I already got it. Now what I want is, let us divide both the sides with density of water. So this will what become, and take G common, bring to the left hand side. So rho W into G. So what will get? Sir, I will get here rho 2 by rho of water H2 plus rho m by rho of water Hm minus rho 1 by rho of water into H1. What is density of matter by density of water? Specific gravity. Density of matter by density of water? Specific gravity. So this implies PA minus PB divided by rho W into G, or let me write here some head H is equal to, what you got? S2 H2 plus SM HM minus S1 H1. In your gate or any exam, normally the options will be in terms of specific gravity. So they'll ask you, what is the difference between the pressure in pipe A and B in terms of head of water. In terms of head of water they'll ask. Means they are asking this PA minus PB by rho WG they are asking. Okay, so that's why I wrote pressure head. The pressure head in terms of water is this S2 H2 minus SMHM minus S1 H1. Okay, so this is what your differential U-tube manometer. Remember, in case of a differential U-tube manometer, the density of whatever the manometric fluid we have used, Sm, is normally greater than the density of both the fluids. Why, sir? Why the density should be more? Okay, for that, little go to your manometer. So we want to know the pressure in this pipe A. Very good. And we had a U-tube. Now what you do, you go and connect it. If you go and connect it, what will happen? Whatever the pressure here, okay, it will run through this U-tube and you will get a fountain here. Means the water liquid is coming out, so you cannot measure pressure. In order to avoid that, what we have done is, we will use some, I have not connected it, we will use some manometric fluid here. we will use some manometric fluid. Some fluid we have used. See, it can push easily air, na? Less density. So, in order to avoid that, I have used some manometric fluid. Okay. So now we will connect it. After connecting, this fluid will go here and will apply a pressure. Because of this, the manometric fluid on the right hand limb will lift. The manometric fluid on the right hand limb will, yes, lift. Let us say it came down by an amount x. So it will lift up also by an amount x. Okay. So what is the difference of height now? So difference of height is 2x. Okay. Now let us say this is the density. Listen carefully. Okay, listen carefully. Suppose the density of this manometric fluid is less than the density of this. What will happen? It will easily push. So I will be needing a bigger manometer, or again the fountain will start. Okay. What if I take this liquid, this manometric liquid, then density of manometric liquid more than the density of water, or density of whatever the fluid here. If I take more, then what? It will resist the pressure some amount. So I won't be getting a fountain, and I need not to go for a bigger bigger manometric tube. See, if your length to diameter you are not maintaining properly, there is a problem of capillarity which associated with manometer. You have to avoid that also. Okay, otherwise you will be having a fault reading, error reading. Understood? That's why the density of the manometric fluid should be more than the density of the liquid here. So in this case, I do not want this to overflow. Hence, the density of my manometric fluid, or the specific gravity of the manometric fluid, should be more than the specific gravity of the liquids inside. Okay? Understood? Very good. This you understood. Why more? Because in inverted U-tube manometer, we need lesser density. Why, sir? What you are telling? Interesting. This is what engineering is. Okay. Now, let us imagine a situation. In this case, I have enough space to place a U-tube manometer. Okay. So that's why I have gone for a vertical U-tube manometer. Now, imagine a case underground. Okay. This is your underground. In this underground, you have two pipes. Okay. Your pipes are going like this. Okay. This is underground and you have two pipes. Now, you have to measure the pressure difference in these two pipes. So, can you connect a U-tube manometer like this in this case? Vertical U-tube manometer? Difficult, because you have to dig. You have to dig a lot, you have to excavate, and then you have to connect this U-tube manometer. Honestly, as an engineer, I won't prefer this. I am not gonna prefer this. Then what we'll do? Instead of going like this, what we'll do is, this is your ground level, we will use a manometer like this. We'll use a manometer like this. Means what? What manometer we are using? U-tube inverted manometer, differential manometer. Understood the application why we need this? U-tube inverted differential manometer. But see, it has some problem also. I can go for only low pressure measurement. I cannot go for high pressure measurement. So that means whatever the manometric fluid I will use here, it has to be lower density compared to the gases which is here. Okay, then only I can, like I can use that in your U-tube, inverted U-tube differential manometer. Okay, again let's go for this is PA. Okay, PA, and it has up to this. Okay, okay, this is my PB. PB is a different fluid, so I am using different color. See, color coding becomes important because you are using so many different fluids. Okay, so this is my S2. Okay, this is my S1. Let us say the height up to what it has gone is H1, and the height up to what it has moved is H2. Okay. Now initially this has air. That means what? When you have connected the manometer, both will start applying pressure. Okay. Because of the pressure applied here, what? It is air, so it also travels, the pressure is equal in all directions. So the same pressure will come and it attack here also. So there is no problem in that. But what is the problem is air is compressible. Problem is what? Problem is what? What is the problem? Sir, problem is compressibility. Problem is compressibility. So when the liquid column on the left hand side will apply a pressure, instead of transmitting the pressure, the air at A will compress. Air at A will compress. That means I will get an error value. That means I will have a error value. Okay. The error may be less, but there will be an error. Because instead of transmitting the pressure to the other side, air has compressed. Air has become compressed. I agree, in your numericals, here they will give air only. But in actual cases, what we do, instead of that, we use a valve. What we use? We use a valve here. Through this valve, first we take out all the air. We take out all the air and we fill with a fluid. We fill with a fluid which has low density, which has low density or specific gravity compared to both the fluids. Okay, understood na? Inverted U-tube is ulta of your both. In the concept it is opposite and in the shape also it is ulta U-tube. Okay, reverse U-tube. Less than both the fluids. Okay, now let me take this as a line. Let this be your height HM. Let this be the height HM. Okay, so same continuous mass of fluid. So pressure at point L will be equal to pressure at R. See, you can take this as a reference, this height also you can take X, Y, Z something and you can go ahead, but that will be little lengthier. That's why the choice of reference becomes very, very important. The choice of reference becomes very, very important. We are trying to save some time. We are trying to minimize the calculation. We want easy work. Okay. So that's why I took the reference here. Okay. Now apply your gauge equation. You know, downward positive, upward negative. Downward positive, upward negative. Okay. So if I write the gauge equation here, what I get? PA minus rho 1 G H1, density here is rho 1, density here is rho 2. Okay, density of this is rho m. Rho 1 G H1, again minus rho m G Hm is equal to PB minus rho 2 G H2. PB minus rho 2. See, I can only take the reference lines once everything is in static nature, means they have attained equilibrium. Of course, after some time they have to attain. Okay. So this implies PA minus PB is equal to rho 1 GH1 plus rho m GHM minus rho 2 GH2 minus rho 2 GH2. Okay, very, very good. Means I already got my difference in pressure. I needed the difference in pressure. I already got my difference in pressure. But what I'll do now is I'll do PA minus PB and I'll divide it with the density of water. Take the common G and put it in the denominator on the left hand side. So what I got now? Rho 1 by rho W H1 plus rho n by rho W Hm minus rho 2 by rho W H2. So this implies I got PA minus PB by rho W G, or let me take it H. Again I told you H means what? This is the difference in pressure we are writing in terms of head of water. Okay, in terms of head of water. Already we have discussed what is head, pressure head and all in our previous chapters. So rho 1 by rho W, that is density of water by density of matter by density of water. What is specific gravity? Specific gravity. So I got my expression in terms of specific gravity, that is your head of water. That is your head of water. Now I hope you understood when we use your differential U-tube manometer, when we use inverted differential U-tube manometer. When we use inverted U-tube differential manometer. Got it? See, again I encourage all of you to ask any doubts in the comment section, please. The demerit of online classes, we do not have one-to-one interaction, so I heavily depend on your feedbacks on the comment section. Okay, so please do leave your feedback on the comment section and ask any doubts you have. Okay, pause the video, note it down. Please pause the video and note it down. Before entering to the micrometer, okay, or piezometer, I want to derive something with the help of a YouTube differential manometer. Okay. Now all the cases we have assumed, or we have told that the pressure at these two pipes are different, yes, and the fluid flowing through these two pipes are also different. But this is the case, this particular case which we are going to discuss now. In this case, the fluid and both the pipes are same. Fluid and both the pipes are same. So this derivation will help you put the formula, get the answer very easily in your exams. Okay, without going for all the derivations. Okay, so that's why one time only we are deriving now. Let us say the fluid passing through at P and PB are having a specific gravity of S. Means the fluid passing is same, but both the fluids are passing at some different pressures. Different pressures but same fluid. Okay. Now you have connected your manometer. After connecting your manometer, okay, I am assuming PA is greater than PB. So this fluid will on the left hand side will push the manometric fluid. That's why there is a rise in the manometric fluid on the right limb. Okay, right limb. So SM is the specific gravity of the manometric fluid. P and PB are the pressure at which it is passing through. This is pressure. So what will be their head? Okay, if the pressure in terms of head, if I will define, this will be HA and HB. Okay, HA and HB. See, let us say P equal to rho G HA and PB is nothing but rho G HB. Okay. Now, so now you write your gauge equation. Write your gauge equation. That is pressure on this left hand side is nothing equal to pressure on the right hand side. Why? Same continuous mass of uniform fluid. Same continuous mass of uniform fluid. So applying Pascal's law, after attaining equilibrium, pressure on the left hand limb will be equal to pressure on the right hand limb. So this implies PA plus. What is this, sir? Okay, S means density is rho. Density is rho both the cases. Okay. So rho G H1. Can I write H1 equal to H2 plus HM? Both are on the same height. Both are on the same height. So instead of H1, I am writing H2 plus HM. Is equal to, here I am having PB plus rho G H2 plus rho M G HM. By this time you must know downward we are writing positive, upward we are writing negative. Okay. So this implies, write the difference, PA minus PB is equal to rho G H2 plus rho M G HM. This will go that side, so it will minus rho G H2 minus rho G HM. So what you are seeing, sir? Rho G H2 cancel. So this implies PA minus PB is equal to rho M G HM minus rho G HM. Rho M G HM minus rho G HM. So now what we'll do, sir? As you always do, divide both the side with respect to density of water. Take gravity constant, bring to the left hand side, which will come to the denominator. So what I got here? Rho M by rho into HM minus rho by rho W into HM. So I got SMHM minus SHM. So I'll come to that. Now PA minus PB. I already wrote PA equal to rho G HA, rho G HB. What do? You put this formula. Rho into G HA minus HB divided by rho W into G. See, G cancel. Rho by rho W, sir, again S, specific gravity. Specific gravity is equal to, what I got here? HM common, I got Sn minus S. HM common, I got Sn minus S. Please see here what I am writing. So this implies this continuation here. S into HA minus HB is equal to, where I can write here. Okay, this I am erasing, this portion I am erasing. Understood? So I need little bigger space. Okay. So this implies what you got? Rho by rho W is S. Okay. Density of matter by density of water is the specific gravity. All into HA minus HB is equal to what I got? HM into SM minus S. Now take this S and divide. So if this is multiplied here, it will go to the right hand side. Division. So HA minus HB. This only I am writing as H. That is difference of pressure head. Difference of pressure head H. Your H is nothing but difference of the pressure head flowing through two pipes. Flowing between two pipes having the same fluid. Two pipes having the same fluid. Okay. So H equal to take S this side. So what you got? SM by S minus 1. This is the formula by sir. This is the formula. What is your H? What is your H? Where H is the difference of pressure head flowing through two different pipes having same fluid. This is very important derivation in differential manometer point of view. You can solve lot of numericals, gate numericals, simply just putting H equal to HM into SM by S minus 1. Where in this formula your SM is greater than S. Okay. In inverted U-tube, in case of your inverted U-tube, where S is greater than SM, or your manometric fluid is less than S, what this formula will become? This formula will become H is equal to HM into 1 by SM, 1 minus SM by S. This is the formula for U-tube manometer. Okay, very good, very good. Pause the video, note it down please. So our next topic is your micromanometer. See, it looks like two single column manometer we have combined. Which is correct. See, देखो, what happens in a micromanometer is, because you have a reservoir here and you have applied, some pressure has been applied, that some pressure applied which is delta H, here is your large area, this is your small area, so there will be a small difference in height, it will magnify here, but the H on the limb will be more. That means you will have a very precise, you will have a more accurate result. More precise and accurate result you can find in your micromanometer. Okay, now let us let us go to this problem now, numerical. So let us say the pressure here is PA in the pipe and the density of the fluid is rho 1. Same fluid is going through your rho 2 as well. Okay, so same fluid is going, which is rho 1. Okay, I am just taking both the pipes, we have same fluid. Now this pipe will apply some pressure here. This pipe also is going to apply some pressure. Correct. And I am assuming pressure at A is greater than pressure B, means this fluid which is there at A will push the liquid here more than the fluid at B. That means we can see, okay, let me use the blue ink. Initially this red dot was my, initially without connected the reference line. Now because I have connected it and PA is greater than PB, this liquid has moved till here. Okay, this has moved till here. Okay, this has moved till here. Okay, and here it got lifted up by same amount. Here it got lifted up by same amount. Okay, let us say the fluid here be density rho 2, same fluid only I am using, rho 2. Okay, which has a density rho 2. Now the interesting thing is, my manometric fluid was here before connecting, or before the pressure that has been applied from A and B. Let us say this was, the blue dot is the initial line of the manometric fluid. The blue dot is the initial manometric fluid of density rho m. Density rho m. Now I have applied here pressure. PA is greater than PB, I am assuming. So that means it will push the manometric fluid by some amount. Let us say it has pushed till here. It has pushed till this level. Okay? It has pushed till this level. Okay? So let the push be here. How much? X. Let the push be X. So same amount will rise here. X depth it came down. So X depth is going to rise in this right column. So it has now this height. X it has come. Okay? Now it has come to this height X. Okay, or let me write X by 2. X by 2. So the total depth of the manometric fluid be X. The total depth of the manometric fluid be X. Okay? We can write HM by 2, HM by 2. Just for easy calculation and all I am taking this. Okay? And so how much depth it has come down? Sir, delta H. So how much depth it has gone up? Sir, delta H. How much? Delta H. Okay? We have already read this area be capital A and area of the tube be small a. We normally know this capital A, area of the reservoir, is much higher compared to the area of the tube. So if I write but how much volume it pushed in the left tube, the fluid from A, same volume only travelled here, na? Yes or no? Same volume only travelled. So if I make the volume balance, capital A multiply the delta H is equal to small a into how much depth it went down? X by 2. How much depth it went down? X by 2. X by 2 of not much significant here. I want to write delta H equal to small a by capital A multiply X by 2. Now, I have told you this capital A is a very big number. Let us say it is 100 or 200 or 300 or 400 times more than the area of this tube. So, we can neglect it. So, delta H we are neglecting it to 0. Nearly delta H we are neglecting it to 0. Hence, now I can write, let's say, this depth be H1 and the depth from here to here, let us say, how much? H2. This depth will be your H2. Okay? Now you understood? Okay? Now we can complete the diagram also. This is the fluid which came up to this. This fluid is came up to this. Okay? So how much is the depth? This depth now. This depth is H1. Okay. H1 plus H2 minus X. Plus H2 minus X. This is your depth. Okay? H1. This is H1. This much is H2 minus X is your this distance. Okay? Understood? Very good. Okay. And this distance. Okay, let me write this H1. I'll write this H2 minus X. Okay. So now, sir, why you are not taking delta H into consideration? Already I have told delta H is very small. Now write your gauge equation. That is pressure on the left hand side equal to pressure on the right hand side. But before writing gauge equation, what you should find? You should find a reference line. You should find a reference line on which you can write the equation. So gauge equation. So this is same continuous mass of fluid, homogeneous fluid. So the pressure at A has to be equal to pressure at B. That's why it attained equilibrium. Fluid is at rest. We are studying fluid statics. Means fluid is at rest. They did their adjustment, they rearranged, and now this is the final position. No movement, nothing. Hence I can go for a Pascal law. Okay. So the pressure at L, left hand limb L, and the pressure at this point, right hand limb R, is same. Okay. So now write your gauge equation. So PA, if I write my gauge equation, PA plus what is this? Rho 1 G H1. Rho 1 G H1. Sir, rho 1 G H1. Next what I have? Rho 2 plus rho 2 G H2 is equal to, see, I have neglected delta H already. I have neglected delta H. Here I am taking H1, from here to here H2. Okay, I have already neglected delta H. Is equal to, go to the right hand side. Right hand side what you have? Right hand side what you have? Sir, we have PV. We have PV plus up to this we have rho 1 G H1. Rho 1 G H1 up to this. Okay, from here what you have? You have different liquid. What is that? Rho 2. What do you have? Rho 2 plus rho 2 G. What is this depth? How much is this depth? Sir, H2 minus X. H2 minus X. Okay. Plus you have the manometric fluid. Manometric fluid rho m G X. Total height of the manometric fluid X. Understood now what we wrote? What we wrote? PB plus rho 1 G H1 plus rho 2 G up to this much only, that is H2 minus X, plus this one, that is rho m G, that is rho m G, how much? X. Okay, rho m G X. So now write the difference. I need the differential pressure PA minus PB. Okay, I can see here rho 1, I can clearly see here rho 1 GH1, rho 1 GH1, so I am cancelling out. Okay, I can see here rho 2 GH2, here also rho 2 GH2. Okay, that I will cancel. Wait, PA minus PB. Here rho 2 GH2 minus rho 2 GX plus rho m GX. Take this that minus rho 2 GH2. Cancel. Rho 2 GH2, rho 2 GH2 cancel. So what I got? PA minus PB. 1, 2, 3, 4, 5, 6. 2 cancel, 2 cancel. So left is 2. Good. So what I got? Rho m GX minus rho 2 GX. Rho m GX minus rho 2 GX. This is my difference in pressure. This is my difference in pressure. Differential pressure. Okay. So what I got? Now what I'll write, sir? You are going to write in terms of head, pressure head in terms of water. Very, very good. So rho W, take G common from here, divide here. Okay. So what you got, sir? We got rho M by rho W into X minus rho 2 by rho W into X. So this one PA minus PB by rho W multiply G, or we call it head. Pressure head in terms of water is equal to density of matter by density of water. So specific gravity Sm minus S2 multiply X. This is your head of water. This is your pressure head in terms of water column for a micromanometer. For a micromanometer. So proof is necessary? No, normally I'll ask you numerical. I am just telling how to proceed. Left hand pressure on the left hand limb must be equal to your pressure on the right hand limb, and you have to proceed accordingly. Sir, what about the density in this case? In this case, now in your micrometer case, your density of manometric fluid should be more than the density of this reservoir fluid, should be greater than the rho 1. Like this. This is the density case here. Okay. So the density of fluid which is passing through the pipes A and B should be the least, and your density of the fluid which is there on the reservoir will be in the middle, and obviously manometric fluid will be having your higher density. Okay, understood? Okay, pause the video and note it down. Pause the video and note it down, please. One thing I want to add is, in your micromanometer you will be needing minimum 2 manometric fluids. Okay, as you can see, rho 2 and rho 3 are your manometric fluids. Okay, remember that. It comes in bit question for RRB, SSC, JE kind of thing, or AE, AEE. It normally doesn't apply for GATE and ESE. Okay, now note it down. Coming to the last topic for today. The last topic for today is your 2 piezometers. Okay, we have already studied simple manometer. Okay, in simple manometer we have studied about piezometer. This is 2 piezometers. Okay, how we are going to measure the difference between 2 piezometers? So before that, I want to just brush up your memory, whoever watching this for the first time, about piezometer, how it was working. See, how the piezometer thing was working is, you have took a container. This container has some liquid. any liquid, okay, any fluid you have to, not air, sorry, water, oil, okay, some you have to, correct. So what will be the, and this has a height h, this has a height h. So what will be pressure at the bottom? Sir, pressure at the bottom is rho g h. Pressure at the bottom will be rho g h. Now what I have done is I have connected a L-shaped bent tube here. I have connected a L-shaped bent thin tube. So what I found from here is when I connected that, the liquid from this side will, see, it should be thin enough and it should not be more broad also. If it is thin and like it should be a moderate one. If it is more thin, there will be capillary issues. Okay, there will be capillary issues. So the fluid will start rising. The fluid will start rising in this liquid medium, and I have shown, array what? It's moving, very good. So I waited until it stops, and I found that the pressure here, okay, pressure at this point, let us say this point is 1 and here the point is 2. The pressure at point 1 and 2 have to be same. Pressure at point 1 is rho gh, so pressure at 2 also rho gh. That means the moving of this liquid stops when a height of h has been achieved. And height of h, sir, this is the same h. Yes, the same h only. So what I found is in order to find a pressure of certain thing, if I have connected a piezometer, the height of the piezometer gives me the pressure of the container there. Okay, so same concept I used for a pipeline cross section. Okay, so last class, if you remember, we have drawn a pipeline like this. Here the fluid may be flowing or static fluid, but it is some pressurized, more than atmospheric pressure. Then at certain point we just connected a piezometer. Okay, so the liquid will start rising. At certain point the liquid will stop rising. This value is h. Suppose h height it has come, so we found that the pressure of the fluid passing in this is rho gh. Same, we took a cross section and we have drawn the cross section view like this. Let us say this is the pressure, okay, and it has load a height of h, so P equal to rho gh. So this was our piezometer. Okay, so now what we are trying to do is we are finding difference of two pipelines. So there is a pipe A, there is a pipe B. Okay, in both the pipe there is some pressurized fluid, or fluid is passing at some certain pressure. Okay, this is your B fluid. Okay, pipe B, and I have connected a piezometer here. Okay, and I have connected another piezometer here. At B also I have connected one more piezometer. Let us say I am assuming PA is greater than PB. So the liquid here, it will rise more. Liquid in this will rise more. Let us say the height being h1. आप यहाँ से लो, आप cross section से भी लो, no issues. Okay, we are finding the pressure of the cross section only, na? So let me write from here to here. Let us say this height is h1. Okay, now here also it will rise some pressure until the pressure is equivalent to the pressure on the pipeline. What I understood from here, the liquid in the piezometer will rise until the pressure is equal to the pressure of the fluid passing in the pipe. Okay, so let us say this height being your h2. Okay, or I got here h1, I got here h2. So they'll ask me what is the difference in pressure. So what is the difference in pressure? They'll ask PA minus PB, assuming both are having same liquid. Okay, so rho 1, rho g. What is the pressure? h1 minus h2. So delta h is the pressure head difference. PA minus PB equal to rho g, h1 minus h2, assuming both are having same fluid. So for what if different fluid? Use rho 1, g common, rho 1 h1 minus rho 2 h2. G common, rho 1 h1 minus rho 2 h2. So this is your piezometer. Two piezometer you can use, and you can measure the difference in pressure. But sir, why it is not widely used? Same problem with the single piezometer. What are the problem? What are the issues? What are the demerits? number 1 बोलो क्या sir? It can only measure low and medium pressure, cannot measure high pressure. Imagine you have only water. Let us say this fluid is passing through water at certain velocity, okay, certain pressure. Let us say 1 bar pressure above the atmospheric it is asking. Means I need a 10.33 meter height. Are you getting my point? So I cannot go for high pressure measurement. How much big length your tube you are gonna make? Okay, so it cannot measure high pressure, only low and medium pressure. Next, can't be used for measuring gas. Can't be used for measuring which pressure? Gas pressure. Why? Obviously gas will flow. It will go and mix with the atmosphere. ठीक है, you can, it's not confined cylinder के gas will stay there. Gas will go and mix in the atmosphere itself. So we cannot use for gas. Then what is third problem? So there can be a capillarity action need to be avoided. You have to avoid capillary action in the tube. Otherwise, you will be having a faulty reading. You will have a more reading. You will be having a more reading. Means there is some error. There will be some error in your original calculations. Okay? So with this, your manometer concepts and theories are over. I hope you understood. See, first we studied simple manometer. In the simple manometer, piezometer, U-tube manometer, okay, single column vertical manometer, inclined manometer, sensitivity of the inclined manometer, these things we have studied. Okay? Then we studied your differential manometer. On the very first only, I started with vertical U-tube differential manometer and difference between inverted U-tube differential manometer. Then we studied micrometer. We understood that for a low pressure difference, okay, or a less pressure difference, your micromanometer will give more precise reading. Micrometer will give more precise reading for a low pressure difference. Okay? Then we studied about piezometer and what are the demerits of piezometer. Correct. In the first lecture also we have studied something about the mechanical gauges. See, mechanical gauges are out of your interest only. I have personally worked in some mechanical gauges, hence I know ki when you go to the industry and all, you will be working more on the mechanical gauges rather than the manometer. You are in academic section, research lab and all, you will be using in manometer, that is for sure. Okay, nothing wrong in that. Okay, so keep learning, keep studying. Next class we are going to do some numericals of manometer. Okay, till then have a great day. Good luck. Thank you. And yes, if you have not subscribed to the channel yet, please do subscribe.